welcome to my shop. It's my first video with voice, so be gentle in critics, because after all English isn't my native language. So let's get on. Today I'm talking about cutting metric threads using a metric dial. My lathe Emco Maximat Super 11 didn't came with this clock, and I decided to try to make it. I don't cut metric threads often, but when I do, I just don't feel very comfortable using the always closed half nut, because I don't know, seems like too much for me. It's just uncomfortable. It's not that bad, but and I don't really have the need to do it often, but there is a time when you need it and you want to do it with as little pain as possible. So I decided to make the clock. As most of you know, for imperial threads the thing is much simpler, because there is only one gear. Here we have, in metric version, we have 3 gears that power the dial. All of the parts are 3D printed. I've recently acquired a 3D printer and added it to my shop, so I thought that I should utilize it and make this. It could be made in steel, but it would need a lot of more work, and this way it's much simpler. For now it's working, so let's see what's inside. Generally speaking, there are 3 parts to print. All of those parts are used existing files. Most of them I just made small modifications just to adapt this to my needs. We need 1 screw, 1 little washer, and these are the main parts. So we have the body. As it can be seen, it is fairly simple, hole through, and 1 slot for adjusting the height, because we have on our shaft we have 3 possible positions for the device. All of it is printed in PLA filament. Maybe now, when I'm thinking about it, maybe the PETG could be even better. For this could last longer, but we shall see how long it will last, because, as I said, I don't use it every day. We have a dial. Dial is also 3D printed, and markings were painted with silver marker. So straightforward. Assembly is simple. Before assembly, I should mention maybe the key part for this is this shaft that have three gears on it, 14, 15 and 16 tooth gears, module 1. And there is a very nice trick that I will show how to print it in one piece, so that whole thing is much more simpler. Actually, it's only one option that you need to check in Cura Slicer when you are printing the part. And later in this video I will show how the thing is working directly on my lathe in cutting threads. So once more, we have the shaft and the housing. The shaft goes in. There is this little washer. Washer is to ensure the distance between this disc dial, so that it doesn't rub against this housing. And all of it is connected through the screw, small Allen wrench, and that's mostly all that there is. There is not much into it, so who is in the need of something like this can make it in their shop. If you have a 3D printer, it's fairly simple. For everyone who wants to have it, write me down in a comment and I can send you STL files ready to print. So you print it and just assemble it. It should be okay for this lathe that's meant to work on a lathe that lead screw has a pitch of 3 millimeters, like my Emco Maximat Super 11. So here we are in FreeCAD to examine the parts individually. Here is our... I won't go much into details because I'm in this video just explaining how the thing works, and all of the files will be available for you who want to have it. You can write me in comments and I will send them for free of charge. It's not a problem. You know how you say, you have to give something back to the community. Only modification of this housing I made. Original housing that is for the imperial dials have only one hole for the mounting screw. Since our in metric variant we have the need to change gears, sometimes we must have 14, 15 or 16 gears in mesh, so there was a need to make the slot instead of one hole. So this is the only modification that I made. It's a fairly simple part. Next thing is this shaft. Shaft is what I've made all new. There is actually, nobody should be intimidated who does not have experience in FreeCAD, because I also didn't have it. I'm using it just for a few months, and actually the learning curve is not that steep and it's possible to overcome every obstacle in the way. Making gears is fairly simple in FreeCAD, so this is it. The shaft have this hole for the screw. Thread inside this hole I didn't print it directly, I just cut it with the tool, because I think that's much better and much more consistent. These are our gears, and there is one thing that in Cura Slicer needs to be made so that it can be printed in this orientation like is standing right now. This is it. Then we have the thread dial that I also made a little modification. It was not tapered. Here we have the original dial, but I found that it was very difficult for me to print it on a 3D printer. I couldn't get the nice finish, so I did these modifications and made it straight. Graduations are 90 degrees, and this one, number 3, is 30 degrees. So it's pretty straightforward. So here we are in Cura. Most important thing for printing this part, this shaft, I will show it now in a moment. For the people who are deep in 3D printing, there's nothing new. It's a fairly simple thing, but since the purpose of my video is for a fellow home shop machinists that are not all together in depth in knowledge with the 3D printing processes, I think that someone might find this useful. So we go File, we open Recent, there's our shaft. In Prepare, it looks like this. Now, it cannot be printed like this. We click it and select face to align the build plate. We want this face to be aligned, and now, before printing everything, you must notice that if you cannot print this like in this orientation just like that, because now these upper gears are practically printed in thin air. So everybody knows that it's not possible to make it like this. So there we have a little option. There is a small option that we can create here in experimental folder in properties for printing, just check this make overhang printable. When we do this and make a slice in G-code, Cura Slicer will make the G-code accordingly that we can see in preview. That will make this, when you are looking at this overhangs, so that upper gears are not printed in the thin air. For the functionality of this part, this has no meaning. It will work just as fine because my part is also printed like that and there was no major problem. Now it is ready to print. All of parts you can have them to be printed in infill 80 to 100%, it doesn't matter. 100% just to make sure that there is enough stiffness and that it will be okay. Also, maybe if I would do it again, and maybe in the future, if I will print again this part, I will make it from PETG, because I think that PETG could be a better material, maybe slightly better than PLA. So that would be all in that part. This is how it looks when it is printed. It should be printed without major issues. Mounting of the dial is pretty simple. All is done with the M8 screw, and the machine has a hole that has this purpose for mounting the dial. So the dial is screwed onto the carriage. It's a number 13 socket wrench. This is how it's done. The device may be always on the machine, just if you don't use it, you disengage it. It can be seen now with the gears. This is the position when the device is disengaged. When we are going to use it, we can adjust the height, mesh the gear that we want to use. Like we said, there are 14, 15 and 16 gears. Let's try to adjust it so that gear 14, the lowest one, is in position. It should be okay. And now we have set the position as it can be seen. The machine is working maybe a little higher. You always position so that the gear that is engaged should be exactly and as near as possible to the center. The center of the lead screw. So for this particular threading dial, we have a table where we can read which gear to use in the dependency of which pitch we are going to cut. For example, let's say we are going to cut 0.7 millimeter pitch, that one here. We must engage 14 tooth gear, and we must engage half nut at the position of 1 and 2, and so on. This is a table. It's available online, so it can be printed and put somewhere in closest. So here we are on the lathe. We are going to test our threading dial. For the test, I'm going to use 16 millimeter aluminum bar. It should be sufficient just for testing it. We are not going to cut the complete thread. We are just going to test does the dial work, and will it match when we are opening and closing the half nut respectively to the lead screw. Now we have our bar that we are going to, and I'm going to do this in lower speed just for the visibility for the camera. I have set my compound 29.5 degrees, and so we may start. For this demonstration I will not use the compound, I will only use our cross slide, because it's another topic to discuss whether to use compound or the cross slide when cutting threads. First we need to clean a little bit our bar just for preparations. So let's go. Maybe at some higher speed. Just a facing cut. And we are going to just straighten it. Nothing fancy. This should be enough. We must take another pass because our aluminum bar is probably a little bit bent. So let's take another 0.2 millimeter. Enough. I'm going to use the marker so that we can see better our thread. I've already squared my thread cutting tool respective to the work piece. That's it. And now we are going to mount the dial. The dial there is one screw, M8, and we are mounting it on the machine. According to the chart, we are going to cut first. We are going to cut our thread in 1.75 millimeter pitch. That calls for 14 tooth gear to be engaged on a lead screw. So it is our lowest gear. So we need to mesh it up. That would be it. Snug a little, not too much. That's it. Then, as we see, it is engaged, and our table says that we should use markings on the dial numbered in 1 and 2 for the 1.75 millimeter pitch. Next thing we need to do is set my quick change gearbox. 1.75 is position C. C3. It's okay. Next thing is find the spot where we can close the half nut and loosen our upper screw and set the dial so it shows 1 or 2. Let's put it on 1. That's it. Open the half nut and try. It spins, so it should be okay. Now put the lathe spindle in lowest gear, lowest speed. We can test, of course, preliminary test can be made, so make sure that we can close the half nut in positions 1 and 2. This is position 2. Position 1. So it closes and should be okay. Then it's a standard procedure. We are starting the lathe. And yes, we have to engage our lead screw. Now that we have done this, now we can start. First, find our 0. It is here. Retract, go back and out. And for the first pass, just for a scratch, we take 0.1 millimeter. And as the tables say, engage at position 1. This is 1. We have a scratch. You may notice that I didn't make lead out for this type of job because it's just this demonstration. It certainly is good practice to make it so. Stop, retract, go back, take a measurement, we take another 0.1 millimeter, and this time we are going to engage it in position 2. This is our position 2. And we have a perfect match. At desired position, disengage, retract, go back. Let's take this time 0.2 millimeters just for fun and engage in whichever is closest, 1 or 2. For this is 1. As it can be seen, we have a perfect match. Our spindle and our lead screw are synchronized, so the threading dial is doing what is his job to do. That's it. Now, when we are not using it, we should disengage it, but for this, now we are not going to open it and close it too many times because there is no need. I'm going to turn off, clean our thread because we are going to test next one. Next pitch that calls for another gear. Put it in higher speed. Let's clean the part. Let's use the marker again. Immediately put it in lower speed. Next on our schedule is to test for the next pitch. We are going to cut thread 2.5 millimeter pitch. For this, our table set calls to engage middle gear here with 15 teeth. So let's do it. When we are setting the dial, we should always make it so that the gear is perpendicular to the axis of our lead screw. It's inside. We can test it. It spins, so it is okay. Now, according to our table, for 2.5 millimeter pitch thread, we need to engage gear 15 teeth and use markings 1 and 3. So our dial must be set when our half nut is closed on position 1 or position 3. We are setting it now. Let's see, position 1. That's it. Test, will it close on 3? Yes, it will. So looks for now that our gear is working as it is supposed to do. Change it to thread cutting tool. And same as before, let's take our measurements. Oh yeah, before that we need to set our change gearbox. Our gearbox is in position C5 for this. For this thread, it needs to be in position 5. C5. Put it in the lowest gear and position. Let's find our 0. This is our 0. Retract, pull out. Let's take first pass 0.1 millimeter. Engage it, our half nut in position 1 or position 3. This time we are going on 3. Go. Retract. Let's take another one. This time we are engaging on position 1. We have a perfect match. So our lead screw and spindle are synchronized completely. Let's take another one. This time another 0.1 and engage in position 3. perfect. So it is correct. Now we could do this all the way, but there is no need for the thread. It's another topic, how to measure it, how to make it to specs, and so on and so on. Now we are going to clean this one up. We have something more to do. A little more. Just another pass. Next we are going to cut 2mm pitch. That's for our gearbox position C4. It's position C4. And our table says we must engage 16th teeth gear. So the dial goes to the lowest position. And markings that we are going to use, in this case, are going to be 1, 2, and 4. So at a convenient place we close the half nut and we can set our upper dial on 1, 2, or 4. This is position 4. The dial works, it spins, so it is meshed with the lead screw. Putting the tool. Slower speed. Find the 0. First pass 0.1mm. So we can engage, as the table says, in 1, 2, and 4 position. Let's try on 1. Okay. Retract. Another 0.1 pass. This time we are going to engage in 2. We have a match. Okay. Retract. another 0.1 pass, but this time we are engaging in at position 4. This is 4, and we have a match. So the table is correct, and most importantly, the thread dial is operational. That's it. Thread looks okay. Synchronization between the spindle and the lead screw is okay. So the device had passed the test. Now, for other pitches metric for this machine, is stated that if they are not in our table, then it can be cut in closing the half nut in whatever position. It doesn't matter. So just for fun, I'm going to test this also. This case, I'm going to disengaging the thread dial because we are not going to use it. And generally, when it's not in use, there is no sense for spinning it, because after all it is all plastic, so it will be worn out. I don't know when it's going to be worn. When it wears out, I'm going to consider, am I going to make another one in metals or just simply print another shaft in plastic. I think that the case is going to be print another one in plastic, because plastic is cheap and there is no need for much time. Cleaning this up. Once more. For example, thread in pitch point of 1 millimeter can be cut without using the threading dial. So let's test this thesis. So for 1 millimeter pitch, gearbox must be in position B5. B5, and we don't need the threading dial. So let's test it. Okay, find our zero. It's this. Go out. .1 millimeter pass. There's our thread. Retract. 0.1. Engage the half nut at will. And we have the match. So it is correct. cutting the thread with using the threading dial, for me, is much more simpler and easier, and I can do it in higher speeds. No one says that it cannot be done with always closed half nut, but for me, I feel much more comfortable when using it lathe this way, and I think my threads are much better come out from the machine in this method than using it the method with always closed half nut. One of the main reasons is this lathe configuration, because there is no spindle brake, and the way of engaging latent power, you can always make a mistake. So this method is much more safer. Overall, the feeling of the control is much bigger for me. That would be all for this video. If you like it, share it, subscribe it. I hope that someone finds this useful.